Hello and welcome to Mobile Warsaw number 23. It is my pleasure to say hello to everyone here, and it is also my pleasure to welcome all the newcomers. So who has not been here before? Maciek, you have been here before. Now, let's go to our sponsors, because as you probably know, we do have sponsors and they paid for the beers. Speaking of which, you can grab a beer or a coffee, I believe, or any soft drink you can imagine at the bar over there. No coupons, just go and ask. So our first sponsor is Allegro, so give it up to Allegro for buying you a round of beer. Woo! Of course, our second sponsor is Mobica, so give it up to Mobica for buying a round of beers. Woo! And last but not least, I would like to thank you, El Passion, because they are not sponsoring the beers, but they are sponsoring videos, and you will be able to watch all Mobile Warsaw talks starting last event, I believe, on our YouTube channel, quite soon. And as usual, we do have a few goodies to hand out. I think we have 2 JetBrains licenses for this event. You can go to Antec, or you actually should if you want to win, and register on the iPad, because otherwise you won't be well considered in the raffle. Yes. And speaking of Antec, he has some more info on the event. Antec.
Okay, so welcome. As always, we are searching for speakers. So if you have a nice talk that you would like to talk about, please contact me or Pavel. We also, yeah, exactly. Website is very nice for that. Also, if you have any suggestions, or maybe you know someone who has a nice topic and you would like him to talk about it, we are very good at like bringing the guys here and making them speak for us. And also, if you have any other suggestions, like we don't like this kind of beer, maybe we can do something about this, please contact us at hello@mobilewarsaw.pl. And have a great meetup.
These are key topics that I have some knowledge. From what is interesting maybe is the application security. I'm working with security, application security for, I think now it will be 5 or 6 years. In creating mobile applications, it will be, I think, about 8. With continuous integration, maybe 1 or 2. Computer graphics, it will be over 12 or 14, something like that. But getting started, let's take a look quickly at agenda. I will not go into much of the details. Idea is generally, this is the quite soft talk about how Android and iOS compares in terms how some processes on these mobile platforms are created, how is the architectural differences between Android and iOS. In general, this presentation is divided into parts. The first part more the architectural one, the second part more the practical one. First question about security generally is why we should consider it, why it is important. Generally because in last years our mobile phones are mine of knowledge about us. On our mobile phones, we pretty much store everything. We have access to bank accounts. We have mobile applications that allows us to make allow us to send money, real money. We have social accounts. We store passwords. We store passwords to some cloud services. We store photos of our ID cards, of our documents. We also have short messages. Pretty often that allow us that this is the second factor to access some other services. There is pretty lot, but do we consider maybe let's think about what would be cost for us if we just lost somewhere our phone? What can happen when we lost our phone? Maybe we leave it at table in pub. If someone get access to that phone, this phone is not locked, he can maybe send some Facebook messages, but maybe he can, yes, take a look, where is your phone? But maybe can do much more harm for us. If we look into security issues, there are three main areas that I will like to cover. We will take a lot of time about this, the third one. There is virus and malwares. We know how it looks like on Android. It's pretty bad. There is a lot of malware. It's pretty easy to create a malware, install a malware on Android devices. But when we think about Apple devices, iOS devices, it's better, but it's not really that great because there are some myths about iOS devices. They are, in fact, there were at least one application that made to App Store that managed to go through review process, and that was stealing the data from the mobile phone. It was find and call. It was back in 2010, 2011, something like that. It's better, definitely, than on Android, but what is pretty important that attacks on iOS devices are more targeted and more sophisticated. For example, let's take a look at X-Agent. There should be X-Agent, but I see that it got cut by Doxet. There is some malware discovered last February. I think that it was discovered by Trendmill, something like that. There is company, security company. This distribution of this malware is pretty low. It's targeted for some specific users, some specific group of users. But you may think how it gets distributed. Apple have a program named Apple Enterprise Program that allow us to sign application and distribute it without App Store. So this is the way. It's pretty easy to revoke the application, revoke the certificate. It's really easy, but as long as the distribution of the application is pretty low, this malware X-Agent have pretty severe consequences when you install it on device. It's impossible to see it, for example, on iOS 7, that such application is even running in background, that there is such application installed. It's definitely better, but even non-jailbroken devices on iOS are somehow vulnerable to some viruses, malwares, and we should make that. We should have that in our mind. There's of course second group of security issues. You probably, if you buy, for example, Android Samsung, those apps can introduce some potential vulnerability problems. They could introduce some bugs. They can even steal our data, and in fact, we can nothing that we can do about it. Even some of the apps can be disabled, but not all of them. If the application is marked as system, it can even be disabled unless we install some custom ROM. But by installing custom ROM, we weaken our device security. It's pretty severe. But what we should talk about is vulnerable apps. It's applications that we made. This is the main responsibility of us developers, that we should make sure that these apps don't present any potential problems to users. I would like to refer to some example. There is, I think that most of you heard about Mailbox from Dropbox. If I remember correctly, this application was released in 2013, something like that. And there were some critical issues with that application. First one is the exposure of core data databases that could be accessed using iExplorer through USB port from the device connected to your Mac. The second problem is that application allowed to, in fact not allowed, it ran JavaScript from attachments from the main messages sorry, not attachments, JavaScripts that got into HTML of email messages. Why this is a problem? Because with JavaScript we expose some kind of interface to the application sandbox. Some application, for example, someone could send you email and he can try to steal some data from your Mailbox application by accessing, for example, some databases, some attachments. But what is more important that it gives the bad reputation to app. For example, there are 2 comments from users using Mailbox. I would love to try my hands on a better Mailbox iOS app that is more secure. I think that by releasing application that contains some potential problems that will later get discovered, we probably lose trust from our user base. They will be, I think that they will not install our application once again, even if we say that this is fixed, because they will not feel safe with that application. They will not use it anymore. This is clearly information about some Android vulnerabilities. Problem is that even if we manage to, if we think that we fixed our application in any possible way, there is also potential vulnerability that came from the system itself. For example, anyone heard about Heartbleed, the famous OpenSSL bug? Many of applications use custom HTTP connection, using OpenSSL, using curl, or something like that, and they use their own compilation of OpenSSL, or maybe they use Android implementation, but it doesn't matter. This is the vulnerability that we can fix. We can prevent it. We only can react once it occurs. This is 68% of top 3 Android apps were vulnerable to Heartbleed by using OpenSSL from Android system. It was not possible to fix unless you updated your Android device, which is what we know pretty hard, because vendors are pretty reluctant to update their firmware, because this is pretty long process. Because once again, Google changes so much between next Android versions that it's pretty impossible to rebase it without any fixes. We had some such problem with one of our projects. This is the latest data from 2015. More than 1,200 popular apps that use OpenSSL and curl, they are still vulnerable to latest freak attack that allows to reduce the security of encryption channel to server. These apps are downloaded over 6 billion times, so it's pretty large use base that can be somehow exposed to some potential problem. But okay, let's go. There is, I think that any security problem we can divide into some, any problem we can divide into some layers. I would like to talk about some security layers in that matter. I will not cover all these cases because we don't have such long time. I will focus on a few of them. First one is the system security. It's the security of system itself. It's what is beneath, maybe not beneath, but what is doing Linux kernel, what is doing Darwin kernel. And there is a few keywords that I would like to talk about. Maybe not into deep details, but I would like to give you a glimpse what is the difference between approach to the system security between Android and iOS. Let's take into consideration the first one, crypto engine. Maybe you heard that all iOS devices are encrypted. Yes, they are encrypted. And crypto engine is the separate coprocessor that does hardware encryption. It's put between NAND flash and between processor itself, and it's being fed with some device-specific key. So if it's online, it's transparent to the application itself. We can't access it. We can't modify it. It's hardware encryption is obligatory. We can disable it. We can even change how it works. We maybe can even know how it works, what cipher it uses. But what is important that crypto engine ensures that memory user data is tied to our device. If we unsolder NAND flash and solder it to other device, it will simply not work because there are different keys. Of course, there is also secure boot. Secure boot allows us to, maybe not us, allows system to ensure that it haven't been tampered. Tampered that someone just connected USB cable to our device, modified system, put their rootkit. It's done pretty good on iOS because there is such feature. On Android, because of fragmentation, it's quite problematic. I think that latest Android 5.0 Lollipop devices should have that enabled by default, but I am not really that sure. I think that maybe some of the vendors will disable it because this is problematic to implement. I think the most problematic is the update part of the process. On Android and on iOS, we have some part of the processor. In documentation, it says that this is the separate processor. It's, on iOS, it's named Secure Enclave. On Android, it's named ARM TrustZone. It's the processor that is specifically used to store some device-specific keys, device-specific identifiers, encryption keys that exposes some pretty basic functions. Functions like, I want you to encrypt me this blob of data, and in the return, I get encrypted blob of data that I can store on my device. It works pretty much the same. For example, on iOS, Secure Enclave is used to store .id fingerprints. They are not stored on user memory, I think user flash, on device flash. It's stored completely in Secure Enclave. Even in Apple Docs says that it's impossible to upgrade Secure Enclave unless we wipe all of its contents. So if you want to upgrade Secure Enclave, the first thing that Apple does, it wipes everything from the Secure Enclave. It means that everything that we simply can't access our data because we lose all the encryption keys to decrypt the user partition. There is the last one element, secure element. But I will get into details about it later when I will tell a few words about payment. I think that everyone heard about jailbreak, routing, custom rooms. With few words, don't do it. It compromises your device security. especially don't do it on iOS. There is only right now Chinese jailbreak. We don't really know what it does before we even jailbreaking. It disables some important security features. It can disable sandboxing of the application. On Android, it disables secure boot if it is enabled. It allows us to run application as root. So in fact, it disables security in SELinux to some extent. Generally, jailbreak is bad, rooting is bad. If you want your data to be secure, don't do it. Never, never, ever. Everyone tells you that. Don't do it. If we move into next layer of security, there is data encryption. There is also two different approaches. On iOS, we have 3 layers. We can say that there are 3 layers. First layer, which I talked about, is full disk encryption. Every iOS device has full disk encryption enabled. We can't do it about it. There's also 2 higher level layers. File data protection, which is used to encrypt individual files of the file system. We can, for example, mark some files that can be decrypted only if users unlocks the device. For example, we run an application, we have our application running, we lock our device, we mark that this file can only be accessed when our device is unlocked. So if we try to read the contents of that file, it will be simply not possible. There is also keychain. Keychain is, I think that everyone heard. It's to store passwords to services. It's to store encryption keys, asymmetric keys. File data protection and keychain, I think that they have pretty similar features. What is important that keychain is on on iOS device is stored in secure data container. It's stored outside application sandboxes. In fact, keychain is managed by separate process. Our data in keychain are encrypted, but the data of keychain are stored in SQLite database. So if you jailbreak your device, you can access passwords stored in keychain, but only those who was created after your device got jailbroken. This is the exactly how it works. If we look at Android, there is quite difference because we also have on Android full disk encryption, but it works pretty different. Full disk encryption on Android is made completely in maybe not user level, it's on software level. It's made by Linux kernel, it's done by the encrypt module. It's bad and good idea. It's hard to tell. It has its advantages and disadvantages, but it makes it some kind of problematic. On right side, there is Nexus 6. This Nexus 6 is one of the first devices with Android 5.0. The problem with that device is that it has pretty weak disk storage performance because CPU in that device doesn't support hardware acceleration of encryption. If we go further, Anantech, who did some benchmark, discovered that Nexus 6 without full disk encryption has disk storage performance about 3 times faster than normal when taken from the box. Because all Android 5.0 devices should have full disk encryption enabled. But this is also pretty interesting because Google changed its policy. When first Android 5.0 got released, they said, okay, from now on, our devices have full disk encryption enabled by default. You can disable it. It's always on. But later with these device problems, they change. I think they change their compliance policy to say it would be nice to have it enabled, but it's not enforcing. Maybe with next generation of the processor, I think that ARM64 already has instructions for that, for hardware acceleration of encryption. There are two other mechanisms in Android. There is APK encryption, but it only used to secure transfer on internet, secure transfer of APK over internet. There is not much to talk about it. There is a similar tool to store keys like on iOS devices. It's named KeyStore, but it works again differently. We'll get back to it. What is nice about Android that all these encryption details are pretty well documented. We'll not go into details because there is some information how is script used, how is hardware-based key used, and what is the algorithm parameters. It's not really important. What is important that this is well documented, and if we want, we can change it anytime we want. But we have to compile your Android. That's the main problem. But when we get back to KeyStore, KeyStore have one main problem that it can store only asymmetric keys, and it got introduced quite recently because with Android 4.3, and not on all devices is hardware-based. There is a fallback method of storing using just pin or some pattern that you draw on screen or something, other factors to secure the key store if it's encrypted using software-based encryption. There is, of course, app security. This is the most interesting part, I think. What is nice about iOS that iOS introduced, I think not introduced, it uses walled garden permission model. It's pretty nice. I really like it. I've been using Android for over a year. I use some custom ROMs with some extra modules for rooted device, just to make sure that my data are safe, my data are private. On iOS, you simply see once application wants to access to contacts, you see that this application wants to access contacts. Do you allow this application or not? You can simply disallow. Application needs to implement the behavior for disallowing access to some components, for example, camera. Of course, all iOS applications are sandboxed. All applications currently use address space layout randomization, so every module of application framework is loaded in random address of this random address of the memory. With introduction of iOS 8, there are a few interesting new features. Application can share preferences, share containers, share keychain items. There is something like app groups. Apple finally introduced some inter-process communication with, for example, NS distribution notified center. Previously, you had to use URLs schemes. It was not nice because you could simply send, but it was hard to receive some result from this operation. If we look into Android, there are, of course, as usual, some similarities. But Android uses something named open permission model. In last year, they even introduced bundling of the permissions because Android has pretty large number of permissions. They are pretty granular for everything that you can read or write contacts. But with that, I saw some reports that they also introduced some potential security issue. that when you install application that have one of the groups, yes, for example, access to photos media files, and if you add permission from that group to your application and push that application to Google Play, then this application will get automatically updated. Previously, you had to confirm this permission, that you really want to add this permission to application. And now, as long as you confirm that photos media files you accept, it will get installed automatically. What I really like about Android is that this permission model is allow us to create our own permissions, that can be assigned to services, content providers, or activities. And permission can be signature locked. Signature is taken from the key store that you use to sign your application. So you can simply create permission to access some service, make this permission signature locked, and as long as you sign your other application with the same key store, this other application will have access to that service, even if it's exported. Sorry, only if it was exported, but some other applications that was signed with different permission will be blocked. We will receive permission denied. There are some other features like user ID-based sharing, so you can create applications that have the same process group name, I think, or user ID name, and these two applications will get the same ID, user ID on system, and they could cross-access their files without any other APIs. But this is application security. There is one more, and not only this one. There is network security. The heartbleed that I said earlier. This is something that we can't control. This is, comes from system, from external libraries. Android, iOS, I think that they expose pretty much the same. There may be some differences in handling web views, but it's not really that important. What is important that with network security, we ensure that we really access the server, the one that we want. We ensure it allows us to ensure that data transferred over wire are encrypted, are confident. No one can decrypt it unless he has private key. And no one can break into our communication, be man in the middle. There is a name of. I said a few words earlier about that. There is privacy control. What is interesting that, again, iOS did it way better than Android. On iOS we have advertising identifier. We have, for now, even application can't read UDIT. It's impossible for application to read some unique device identifier. So it's impossible for applications for advertisement to track our activity. But there is also the second thing, that with this wallet garden permission model, application can also access contacts without our permission. We need to allow application to do that. On Android, it's much harder because Google services introduced something like advertising ID, but there is a lot of more surface to fingerprint our device. An application can use, for example, IMEI, IMSI from the SIM card. They can use Wi-Fi MAC address as long as it has access to that permission. We simply can't block that. There are some, of course, modules, but it requires that our device is rooted or uses some custom room. There are two to note. First one is cyanogen. There is privacy guard. Privacy guard just overrides access to all sensitive APIs. It simply feeds your application with fake contacts, fake call logs, fake geolocalization, and it does that on system level. Application can't simply read real contacts unless you mark that application as trusted. There is a second module. Its name is privacy. It allows us to block any individual permission on any application. We get prompted once, for example, the application open connection to some server. We can, for example, track which application use, for example, Crashlytics. It's really simple because we get pop-up on the main screen once the application makes connection to Crashlytics, and we can allow the application or disallow this. There's two different approaches to payments. First one is the one that Apple, I think that, different way. Google had three approaches to payments, and Apple used the first one used by Google. First one used by Google was with use of the special processor named Secure Element. Secure Element is the small processor that can run some simple cardlets. Cardlets are a simple Java application with its own stack, with its own memory. On this coprocessor, anyone, in that case Google, who had access to 3D keys, could install payment application. This payment application was responsible, of course, as it is on any chip enabled card or PayPass. It's responsible for signing some transactions and sending data to the terminal. Google later decided to drop the secure element. They allowed the carriers to use SIM cards. You probably heard about T-Mobile offering some special SIM NFC-enabled card that you could pay with it. But it's quite problematic because it requires you to it requires many companies to connect their services. They require carriers, they require vendors to provide special firmware, they require banks or maybe even payment operators. So they decide to drop that also and introduce something named host card emulation. Host card emulation is simply secure element in cloud. In that way, an NFC-enabled Android mobile phone can simply install application that can use NFC. For example, POP is in Poland, and POP uses NFC with secure element in cloud. Data is transmitted over the internet, and you can pay with your mobile phone using NFC PayPass just by registering to your mobile account without buying an additional SIM card. This is everything from the architectural perspective, but what is next and what to do? There is one organization, it's named Open Web Application Security Project. They provide a list of 10 top mobile risks. Maybe it's not really that important what is on that list, because I think that we will cover most of them in the best practices. But I would like to ask ourselves a few questions. How we create application, how we decide that this application is indeed secure. There are first three one. Do we store sensitive data securely? What do we have to store on the device? Maybe we can store just some session key, maybe some user identifier. Do we really have to store username and password to access to the service? How and when do we have to access this data? Do we have to access it when user unlocks the device and our application is our foreground, or maybe some other scenarios? How do we indeed sure that we are indeed talking to our server? We are talking to someone, but how we ensure that this is our server, that this is our trusted server that is serving some important data, for example, verifies our payments from the Apple. It's really important how we construct the API, how we authenticate ourselves to the server. How do we handle application logs? Do we have them enabled in release? If yes, do we put to them some sensitive data, usernames, password, maybe HTTP request that we send to the server? How do we implement user interface? There is a few cases. Maybe we have some registration form, a login form. Maybe it would be wise to divide that registration form into multiple steps, just to prevent from taking screenshots of the all user data just from one screen. Do we obfuscate our application? It's pretty controversial now, whether we should obfuscate or not. But current tools, for example, ProGuard, it's pretty well documented. Everyone uses it. Even if we use some libraries, there is pretty much definition for ProGuard for everything. There is also one more question. Can other apps access parts of our application? I think about scenario when we have some exported services from the Android application, or maybe we have to run HTTP server from our application just to serve some media content. Does that HTTP server get exposed over a Wi-Fi connection? Maybe anyone in your home network can access that web server? This is kind of questions that we need to ask ourselves when we evaluate whether our application is secure. In general, there are a few best practices that you can follow to maybe not, you will never be 100% sure, but it will be 17, maybe 60. It will be better than nothing, I think. These best practices are in these 6 points. But what is, I think, pretty much important is that in the end, the best is to try to crack your application. It's not really that hard. When you try to crack your application, you get you get better to know how the potential person from the other side will try to break your application, what will be able to do with it, with the data that you expose. You can also take the incremental approach. I think that I will try to crack application and see whether I store the data securely. What I can do with the cracked application, how it will be, how hard it will be to get the password from the application, for example. About the storing data, there are also a few tips what needs to be done. Generally, be careful what you store in NS user defaults or shell preferences, because they are not encrypted, they are written in plain text. In most cases, they are readable for all. On iOS, never use file protection none. There is pretty good file protection complete, is file system encryption. But if you, for some reason, you need to use that with care. But what to do on Android devices? There is no file data protection on Android. We can only create some custom encryption to securely store files. But where to store key? We can use key store to encrypt the key and store the encrypted key in the shared preferences. It's completely safe because we have some level of encryption. There is also pretty good SQL cipher for SQLite databases. It's pretty thin layer with iOS encryption that makes sure that all data in your SQLite database are encrypted. They are encrypted on block level beneath the SQLite data structure. This SQLite database encryption is filled with single password. Pretty common mistake is also that some developers make some files word readable, so an application can read some data. If you look into some public reports about vulnerabilities from the major companies, at least a few of them had problem with writing word readable data. The main problem is that when you use NDK from Android native development kit, you write some parts of the application in C, C++. By default, fopen writes all files with word readable. Make sure that there is everything done okay. If we look into storing some sensitive data, keychain is really simple to use. There is a keychain item wrapper generated. I will send the slide later so you will see what is written here. But what is really important that there is some keychain item wrapper from Apple. Apple provides two files. One is header, second one is implementation. And you simply access account name, and second one you access password. The same way it goes to storing account name and storing the password. It's really that simple. You just have to do it. You do it the same way how you store it in NS user defaults. It's maybe even simpler. It's not that easy for Android, but it's still doable. For Android, because of the key store is really great, but you have to. Yes, this is really simple, but it's not really important what is written here. It's important what I say. On Android, you have to generate asymmetric key pair and use that key pair to encrypt some data and store this encrypted data in shared preferences. It's a few lines more, but it comes to the same outcome. But storing sensitive data is one thing. We should also ensure that we transmit the data securely. It's really recommended to use in network transport, HTTPS, some strong encryption algorithms. There were at least a few cases, for Android, for example, there were cases where developers of Android changed the order of preferred ciphers when the weakest one possible was at the front of the list. That's the main problem. There is also certificate binding. You can use also own certification authority, but it's getting harder with each of these steps. These first two are really simple. To use strong encryption on iOS, this code will work, but most likely it will not pass App Store review process because it uses private API, but it's still doable. We limit cipher suite to some pretty strong ciphers using Diffie-Hellman protocol. For you that don't know what is Diffie-Hellman, Diffie-Hellman allow us to ensure that anyone, even if he possesses the private key, will be unable to decrypt the transmission. Because the Diffie-Hellman generates ephemeral keys for the connection, for the specific connection. For example, on Android, it works without any glitch. You just simply Ctrl-C, Ctrl-V code and it works. Maybe just maybe without this RC4SH, because this is the weak cipher. But the idea is the same. Most of you probably use AF networking. There is certificate pinning. Certificate pinning, there are in fact two modes of certificate pinning. One is that we bind to certificate itself, and the second one is that we bind to public key. First one has one disadvantage, that if the certificate expires, we need to, before the certificate expires, we need to provide the user new application with new certificate bundled. But if we don't do it, he will be unable to access the application server. With public key, we bind to the public and private key. We bind to the key that is signing our certificate. So we bind to different factor. If we look into something different, certificate contains expiration date, public key is used to sign the certificate. This is the generalization about that problem. It's very simple also on Android. There is, we need to override the trust manager, verify the public key. It's really that simple. So you just have to Control-C, Control-V, and put there your public key, and it works. And it's really enhances the security of your application. What is important that you need to consider how you handle sensitive information in your application. It's advised to mark our text fields with secure flag if they indeed contain sensitive information. In some fields that you think there is name or last name, maybe disable autocorrection. It's also pretty often that we need to disable screenshots on some activities. On Android, there is flag secure of activity. If a user will take screenshot of the activity with flag secure enabled, he will only see the logo of the application, not the content itself. It's much harder on iOS, but it's still doable. I also found that's advised that it's wise to clear pasteboard if we use that in application when we leave the application, when application goes to background. Most of you probably use some Facebook keys or other keys. It's also nice to hide that API keys. But I discourage you from using some public libraries. It doesn't have to be so sophisticated. We just need to encrypt some API key with some factor that we know, split that into different fields and merge that, decrypt, and that's all. What is important that in order to gain that API key, attacker will have to look into application code. He will not access that API key just by looking into strings that is defined in application. Of course, there are also other things that you need to be careful. You need to be careful with using web views. Web views contains JavaScript, can run JavaScript. You can expose some interfaces to web views over JavaScript. This can potentially lead to some vulnerabilities that it will be hard to overcome. I suggest to completely wipe logs for these. It's pretty standard procedure. It's really simple. On iOS, maybe you can redefine NSLog method. On Android, there is ProGuard, which can wipe invocation of some methods. And of course, I also suggest to obfuscate your application. Maybe not in all cases, but it's really simple to do it. But what is really important that to better understand the security of our application, we need to teach ourselves. There are at least a few exemplary programs. One is the vulnerable Android app, application that contains wide range of potential security issues. Second one is iGoat project, but the best teaching is to try to crack your application, because you can see from the other perspective what information are exposed from the attacker. There are also, of course, plenty of the tools to crack applications. These are for Android. Błażej, who will talk within a few minutes, will tell you more about iOS tools. The most popular, I think, most probably is JDGUI. Anyone who had to look into some application code, he probably used AndroGuard, maybe he used Dex2Jar, czyli I think that ability to convert Android application to Java application and then use JDGUI to decompile Java code. I think that's all. Thank you for your attention. If you have any questions,